Hi everyone, this video is going to take a look at a problem from section 3.4, rational functions. Our particular goal with this question is to take a rational function, as you can see is written up in the upper left-hand corner in black, and we want to go ahead and translate it into a visual or a graphic, or we want to graph it. So what I've gone ahead and done is I've put my coordinate plane on the right hand side over here. What I would suggest doing is pausing the video to grab either some graph paper or to do a pretty good sketch with an X and a Y axis on it. Also, what I have on the left hand side, multicolored, is going to be kind of our checklist, and I've put it in a specific order. I find that in order to graph and make sure that I don't miss any of the components in order to create an accurate graph, I found that putting it in this particular order helps me keep track of everything. So one of the first things that I would suggest doing is take a look at the function, and if it isn't factored already, take the time to factor both the numerator and the denominator. In this case, this problem is already done for us, so we're good. We're done here. We didn't have to do anything. So the next thing that we want to do is we want to check to see if this graph will potentially have any holes in it. In other words, a hole is where there's just one coordinate point where it's kind of like, I don't know, like the Bermuda Triangle or something along those lines, where if you enter into that area, just nothing exists. Mathematically speaking, in this case, it's just this point can't support anything. It's undefined here, or it gives you a false statement. Or if you recall from class, that false statement that we get is this notion of 0 being divided by 0. So in this case, we would be looking to see if any of these binomial factors in the numerator matches identically with any of the factors in the denominator. In this case, as you can see, none of them match up, so this means that there is not going to be a hole here. So let's go ahead and clear those arrows out, and so I checked, there won't be any, so I'm good to go. So the next thing that we're going to do is we want to go ahead and try to find the vertical asymptote. And to find your vertical asymptotes, you are going to want to refer to the denominator of your rational function. So in this case, finding the vertical asymptote is basically asking yourself, what restrictions am I going to have that would make my rational function undefined or inaccurate or impossible? And as we've said since chapter 1, we cannot have a fraction with a 0 in the denominator. So that's why we are going to go ahead and just work with the x plus 2 squared, set that equal to 0, and then the x minus 4, and set that equal to 0. And as we go through, we can go ahead and start solving. And these are relatively light steps. So things that we've been working with from the very beginning of algebra are still useful. These simple tools help us solve more complex problems. So we have x is equal to -2, and we also have x is equal to +4. So I'm going to go ahead and etch those in right now. So, and again, vertical asymptotes are usually denoted by a dashed line or a dotted line. Okay, and something else to kind of keep in mind when we are doing this is I want you to take a look at the degrees of each of these binomial factors. So the fact that x plus 2 has an even degree is going to tell me that the short-run behaviors as the function approaches those vertical asymptotes, I'm going to have that the graph will go in the same direction. And the fact that the binomial factor of x minus 4 has a degree of 1, and we say that it's a 1 because we haven't explicitly written any sort of exponent next to it, since it's odd, we will say that the graph will go in opposite directions. Okay, so we're going to save those for later. All right. So let me clear those out so we don't need to see that. Okay, so we have all the information that we need for the vertical asymptotes. Now we're going to go to our y-intercept. Y-intercepts are relatively quick and easy to work through, and I'm going to have to scoot this up. I'm going to be moving back and forth on my sheet here as I continue to work. Okay, so my y-intercept says that we're going to put 0 in for x into this function. So I have 0 minus 1 times the quantity of 0 plus 3 times the quantity of 0 minus 5 all over the quantity of 0 plus 2 squared times the quantity of 0 minus 4. So as we go through and clean this up, we have negative 1 times 3 times negative 5. So basically I'm just doing that addition or subtraction that we're seeing here. 2 squared times negative 4. This cleans up further, so the product in the numerator is going to be a positive 15, and then the final product in the denominator is going to end up being negative 16. So I have a y-intercept at 0, negative 15 sixteenths. So if we go over and plot that, that's essentially pretty close to negative 1. So again, we're just going to do some sort of estimation here. So my y-intercept is located there. The next thing that we are going to want to do is the x-intercept. So x-intercept means that instead of putting 0 in for every x variable that we see, we're going to put 0 in for y. So if I do that, then I have 0 is equal to the quantity of x minus 1 times the quantity of x plus 3 times the quantity of x minus 5 all over the quantity of x minus 2 squared times the quantity of x minus 4. So again, the nice thing is even though this looks intimidating when you do the setup, it actually cleans up relatively fast. Because what we have to do here is we have to multiply both sides by the values that are situated in the numerator, because again, we want to clear everything. And I apologize, this is going to be a little bit crammed, but this x minus 2 squared times x minus 4 is being multiplied by that 0. Well, any sort of multiplication that has a 0 in it is going to cause it to 0 out. So what we're left here with is 0 is equal to x minus 1 times the quantity x plus 3 times the quantity x minus 5. And again, just to remind you, we technically have this over 1, so the product that you see in the bottom is going to cancel out with its identical product in the top. Well, now we have 0 is equal to x minus 1 times x plus 3 times x minus 5. All three of those quote-unquote numbers or quantities are giving us a result of 0. So logically we can say, well, if this entire multiplication that you're seeing here equals 0, then it stands to reason that 1, 2, or all three of these numbers that we have here, these quantities, should be equal to 0. So we will solve for each one. And then we get x is equal to 1, x is equal to negative 3, x is equal to 5. And since we're talking about horizontal intercepts, or x-intercepts, pardon my mistake there, we will get the following coordinate points. So let's go ahead and plot those. So we have one at 1, 0. We have one at negative 3. We have one at 5. Okay. So, lastly, we're going to go ahead and figure out the horizontal asymptote. So I'm going to come down here just to give myself a little bit of space, and then once I'm done, I'll draw it up more. So recall that you wanted to take a look at the degrees of the top and the degree of the bottom. So hopefully you've had this written down as you've been following along. So the degree of the top ended up being 3, and the degree of the bottom ended up being 3. And the reason being is if you were to add up all the degrees of your binomial factors, so if you add up the fact that, let me go back to the visual so you can see. So I have a degree of 1 here, a degree of 1 here, and a degree of 1 here. So that means that I have a degree of 3 in the numerator, and then I have a degree of 2 here, and a degree of 1 here. So that means I also have a degree of 3 in the denominator. So coming back down here, that means since the degree in the numerator and denominator equal each other, then in order to find out what the horizontal asymptote is we take the lead coefficient of the top and the lead coefficient of the bottom. Okay, so slingshotting back up there. As you can see, there is no lead coefficient that we visibly can see. The lead coefficient we usually denote as an A whenever we've solved these in previous problems. So the fact that you don't see any sort of A's in here tells me that the lead coefficient must just be 1. So that means that we have 1 over 1, or simply our horizontal asymptote is just at y is equal to 1. Okay, so I'm going to go ahead and etch that in. Again, using a dotted line. Sorry, that's a little bit wavy. Okay, so the last and final step here is we want to connect all of it together. So what I want to do here is I want to note that my rational function, you can use test points here in order to actually go ahead and figure out what direction everything is going in. But what you can also do is you can also consult your calculator to kind of make sure that you have the general sketch correctly, or you can start using intuition because we ultimately just want a rough sketch. So as you can see here, I'm going to look over in this area here, and I note that I have my x-intercept at x is equal to 5. So I know it's going to hug the horizontal asymptote, and it's going to pass through and hug the vertical. And again, I know this because, let me skip down here. We had noted that all of the degrees for our binomial factors here were 1. So that means that each time we are going to cut through them. We're not going to bounce or slither, as we kind of discussed in class. So we also noted that for this particular vertical asymptote at x is equal to 4, things are going to go in the opposite direction. So that means that since this one went down, this one must be going up. So I'm going to hug this vertical asymptote. I am going to cut through the horizontal asymptote here, but remember that when it's closer to the origin, it's weaker. So I am allowed to cut through here. If it were further out or, heading out further towards negative infinity or positive infinity, that's where it's stronger and I'm not going to be able to cut through it. So I'm going to cut through that horizontal intercept, or my x-intercept. I'm going to hit the vertical, or y-intercept, and it tells me that I'm probably going to be going down here, okay? Because remember, we don't have any sort of rules for cutting or bouncing or anything like that in our y-intercepts. I'm going to add my arrows. And lastly, we had said that at this particular vertical asymptote, things would be going in the same direction. So that means that since this area right here is going down, I must also be going down. I'm going to cut through and then hug the vertical, or sorry, the horizontal asymptote. So here's a rough sketch. If you all do have any questions or if this video was not helpful, please let me know and I will go back and fix it.